Greetings, AP Chemistry students. Today we're going to be talking about polarity of bonds and polarity of molecules. But before we do that, the first thing I want to say is I want to share this statement with you because we've been working with the Lewis model, also known as the localized electron model, where electron pairs are associated with specific atoms. And that breaks down a little bit when we get into compounds that involve resonance structures, and we have to draw those because that doesn't fit very well with the model of the atom we've been using, the Lewis model. So there is the molecular orbital theory, which describes covalent bonding in a different way that's broader and takes into account a lot more of the nuances. However, it's more difficult to understand and it's not predictive of things like molecule shapes and whether something's polar or nonpolar and the arrangement of bonds as well. It does a better job of describing the electrons, but we're not going to learn molecular orbital theory. If you want to learn more about it, there's plenty of research you can do online. If you take an advanced chemistry class in college, you will probably learn about it, but we're not going to. So, on to bond polarity. Bonds between atoms of similar electronegativities are nonpolar. In other words, they equally share their electrons. And the hydrogen carbon bond is considered to be nonpolar, even though carbon is a little more electronegative. It's close enough that we consider essentially if a compound only has hydrogen and carbon in it, we treat it as if it is a nonpolar molecule. Anytime there's a difference in electronegativities, there is some degree of polar characteristics to that molecule. So, polar covalent bonds are the results of having differences in electronegativity. And the atom with a higher electronegativity pulls the electrons closer to itself, which gives it a partial negative charge because it's got the electrons are spending more time with the more electronegative element. And that forms what's called a dipole. Dipole meaning there's two poles, a negative and a positive, just like magnets have north and south poles. And the greater differences in electronegativity, the greater the bond dipoles, the more polar those bonds are. And there is a continuum that exists from nonpolar covalent to polar covalent to ionic bonding, where essentially you go from perfectly equal sharing as nonpolar covalent, then you've got unequal sharing becomes polar, and the more unequal it gets, eventually it's no longer considered really sharing, is that one atom has given the electrons to the other, and that's the ionic bonding. So there's not hard and fast cutoffs. It's a continuum. It's a spectrum, if you will. Right. Now, some other things to note. Differences in electronegativity are not the only factor in determining whether you're talking about a covalent bond or an ionic bond, because generally speaking, if a bond involves a metal, something on the left side of the staircase, and a non-metal on the right side, we consider it to be ionic. And if it's bonds just between nonmetals, we consider it to be covalent. So we'll have to actually examine the properties of the compound to see whether it better fits as an ionic or a covalent compound. And next week, we'll talk more about what those properties of ionic versus covalent compounds are. Now, this shows a extremely polar molecule here, hydrogen fluoride. Fluorine is extremely electronegative, so it will pull those electrons closer to itself, whereas hydrogen would be electropositive or electron deficient in some way. The electron spends more time with the fluorine than the hydrogen. If we were to draw this out, hydrogen, fluorine. Fluorine already has a bunch of electrons around it, and it's taking this pair of electrons that it's got and pulling it closer to itself, making it somewhat negative, the hydrogen somewhat positive. The way we represent this dipole is essentially we draw a plus sign and then we point an arrow towards the negative end. So that represents the hydrogen is positive, the fluorine is negative. That's how we would represent a dipole. The next, all right, so that's just a single molecule. Now, we can identify dipoles based off of differences in electronegativity. And again, we're going to simplify things. Unless it's two of the exact same atom or it's hydrogen and carbon, there's going to be some type of dipole moment because one atom will be more electronegative than the other. So, dipole moments for a molecule occur in molecules that have distinct regions of positive charge and negative charge. And this occurs when you have asymmetrical polar bonds or uneven distribution of electrons within the molecule. And so molecules that have a net dipole moment are polar molecules. For instance, it's possible to have polar bonds in a molecule, but since the molecule is symmetrical, it cancels itself out. We'll look at some examples of that. So here is water. Water has a partially positive charge on the hydrogens and some negative charges on the oxygen. This right here, by the way, is the symbol that's the Greek letter delta. So it's a little bit positive charge, a little bit negative charge. It's not a full on positive and negative like with ions, but the oxygen's more electronegative. It pulls the electrons towards itself. And so if we were to draw the individual dipoles, it would look like that and like that. And when you add them up, you get this one that's represented right here in the middle. So this end of the molecule is more positive. This end is more negative. So it makes water polar. In our next unit, we'll see that has huge significance for all sorts of things that we'll do in chemistry. And this shows the electron distribution. The electrons spend more time around the oxygen. So we'll take a look at another example. This is ammonia, which is trigonal pyramidal. There's a little bit of a dipole going on there. It's positive with the hydrogens, it's negative at the top. If we were to draw out this as a Lewis structure with NH3, you would have that, and essentially the negative charge is on top where the nitrogen is, the positive charge is on the bottom where the hydrogens are. So there is a negative end and a positive end, making NH3 also be a polar molecule. So let's take a look at carbon dioxide. This is an interesting one. The carbon oxygen bond is polar. Oxygen is more electronegative than carbon. However, since this molecule is linear, you'll notice that these two dipoles cancel each other out. So we have polar bonds, but the molecule itself is nonpolar. This is less like a magnet, because magnets have a north pole on one end and a south pole on the other end. This is more like an Oreo cookie, where it's negative on the outside with some positive cream filling in the middle. Right? So this is a non-polar molecule. It does not have a net dipole moment. These dipoles cancel each other out. Here we have hydrogen chloride. This is obviously very polar. Chlorine is much more electronegative than hydrogen. Sulfur trioxide. This molecule, it's trigonal planar. It's completely flat. Oxygen is more electronegative than sulfur. But the way these dipoles are arranged, they are essentially, it's like if you had three people pulling on three ropes that are tied together at the center and they all pull equally strongly, nothing ends up moving because they're, if you take physics class, you'll see that these vectors essentially cancel each other out. They're pulling, but they cancel themselves out. So there's no overall negative end versus positive end. It's positive in the middle and negative on the outside, which is not at all like a magnet. So it's nonpolar. Right. And we'll see if I've got one more example. My computer is starting to freeze up on me. All right, come on here. CH4 methane. Let's see what we've got. Whoops, went too far. Oh, where we go? CH4 methane. It's similar. It's got four hydrogens. Also, this molecule is relatively nonpolar because it's just carbons and hydrogens. So even if the hydrogens and carbons had significant differences in electronegativity, the molecule would still be nonpolar because the dipoles don't cancel each other out. And then the last one, H2S, this molecule is bent very much like water. So the hydrogen is going to be the positive end, the sulfur the negative end. So this is a polar molecule as well.